The first development that led to the solution of these difficulties was Planck's introduction to the concept of the quantum. As a result of the physicist's studies of black body radiation during the closing years of the 19th century, at a body of moderately high temperature, red heat gives off most of the radiation in the low frequency regions. A body at a higher temperature, white heat, gives off more radiation in higher frequencies. During the 1980s, physicists conducted detailed quantum studies of these and expressed the results in a series of curves or graphs. The classical theory predicted an altogether different set of curves from most actually observed. What he did was to devise mathematical formula that described the curves exactly. He then deducted a physical hypothesis that could explain the formula. The next important developments in quantum mechanics were the work of Albert Einstein. He used Planck's concept of the quantum to explain certain properties of the photoelectric effect, an experimentally observed phenomenon in which electrons are emitted from metal surfaces when radiation falls from these surfaces. According to the classical theory, the energy as measured voltage of emitted electrons should be proportional to the intensity of the radiation. The energy of the electrons was found to be independent of intensity of radiation, which determined only the number of electrons emitted and to depend solely on the frequency of radiation. The higher the frequency of the incident radiation, the greater is the electron energy. Below a certain critical frequency, no electrons are emitted. These were explained by Einstein by assuming that a single quantum of radiant energy ejects a single electron from the metal. According to the classical theory of an atom, as described by Rutherford, is unstable. This difficulty led the Danish physicist Niels Bohr in 1913 to assume that in atom the classical theory does not hold and that electrons move in fixed orbits. Every change in an orbit by the electron corresponds to the absorption or emission of a quantum radiation. The application of Bohr's theory to atoms with more than one electron proved difficult. Schrödinger succeeded in showing that wave mechanics and matrix mechanics are different mathematical versions of the same theory, now called quantum mechanics. Even for the simple hydrogen atom, which consists of two particles, both mathematical interpretations are extremely complex. The simplest atom, helium, has three particles, and even in the relatively simple mathematics of classical dynamics, the three-body problem is not entirely solvable. The energy levels can be calculated accurately, however, even if not exactly. The impossibility of pinpointing an electron at any precise time was analyzed by Werner Heisenberg, who in 1927 formulated the uncertainty principle. This principle states the impossibility of specifying the precise position and momentum of any particle. Knowing about the position and velocity are said to be complementary, that is, they cannot be precise at the same time. This principle is also fundamental to the understanding of the quantum mechanics. This is the generally accepted today. The wavelength and particle character of electromagnetic radiation can be understood as two complementary particles of radiation.